We present SGHR, robust multi-view point cloud registration with reliable pose graph initialization and history reweighting. Compared to existing multi-view registration methods, SGHR proposes a sparse pose graph construction method that significantly improves registration efficiency while reducing the impact of outlier pairwise registrations. In addition, we propose a history reweighting function, which further enhances the registration reliability and accuracy by combining with the iteratively reweighted least square algorithm. The experimental results show that SGHR achieved a higher registration recall and exhibits strong generalization ability on both indoor and outdoor datasets. Moreover, all the above state-of-the-art performances of our method only require about 30% pairwise registrations of existing multi-view point cloud registration methods, which demonstrates our computation efficiency. Next, we will provide a detailed introduction of SGHR. Given n unaligned partial point clouds, multi-view registration aims to simultaneously register all these point clouds to get a complete scene reconstruction, by recovering the absolute pose of each point cloud scan in the underlying coordinate system. Specifically, most existing multi-view registration methods first construct a dense pose graph by associating any 2 point clouds and use it to solve for the absolute pose of each point cloud scan, Ti, in the underlying coordinate system. In the pose graph, the relative pose between any 2 point clouds is estimated using pairwise registration methods and stored in the corresponding edges of the pose graph. By estimating the relative poses between all CN2 pairs of point clouds, we can construct CN2 equations and use the iteratively reweighted least square algorithm to calculate the absolute scan poses, Ti. However, there are two problems with this approach. Firstly, constructing a dense pose graph requires CN2 pairwise registrations, resulting in an n-squared level of computational complexity. Additionally, low overlap or non-overlapping point cloud pairs lead to a large number of erroneous pairwise relative poses, called outliers, which can cause the subsequent IRLS-based absolute position and orientation estimation to become trapped in local minima. Based on these observations, SGHR proposes a sparse graph construction strategy, which only requires recovering less than nk pairwise relationships in the sparse pose graph, resulting in a linear computational complexity of n. Moreover, most of these relationships are correct for coming from high overlap point cloud pairs. Furthermore, we propose the history reweighting IRLS method, which can further improve the reliability and accuracy of multi-view point cloud registration. Specifically, in the sparse graph construction process, SGHR first estimates a global feature f for each point cloud, which is derived from the aggregation of local features of the point cloud. Here, we choose to use Yoho as the local feature, which can be further used for pairwise registration. Subsequently, we can efficiently estimate the overlap between any 2 point clouds by correlating their global features, and supervise the consistency between estimated and ground truth overlap during training to enhance the global feature extractor. During testing, when constructing the sparse pose graph for each point cloud, we only connect k point cloud pairs with the top k estimated overlap to it, resulting in less than nk edges with high estimated overlap ratios. Then we perform pairwise registration on these edges to recover the relative poses for pose graph initialization. In history reweighting IRLS, the input is the sparse pose graph constructed earlier, and the output is the absolute pose of each point cloud. First, the edge weights in the sparse graph are initialized, taking into account the estimated overlap S and the ransack inlier correspondence count R. Then, the pose synchronization algorithm is used to estimate the absolute pose of each point cloud from the weighted sparse pose graph. However, due to the presence of outlier edges in the pose graph, the pose estimation is not accurate. To reduce the weight of these outlier edges, we propose the history edge reweighting function, which robustly and gradually penalizes the edges with larger synchronization errors and recalculates the edge weights by iteratively repeating step 2 and step 3. The graph edge weights eventually converge to a stable solution, allowing us to identify and remove outliers in the sparse pose graph. Finally, the correct scan poses are computed. We demonstrated the effectiveness of SGHR through extensive quantitative, qualitative, and ablation experiments. Firstly, on indoor 3D match and 3D low match datasets, SGHR achieved 11% and 6.2% improvements in registration recall, respectively, with only 20% of pairwise registrations compared to existing multi-view registration methods. Moreover, SGHR achieved a speed improvement of 61 to 160 seconds in each 3D match scene, benefiting from the proposed sparse pose graph construction. When generalized to the ScanNet dataset, SGHR achieved lower rotation and translation errors by 12.8% and 13.8%, respectively, using only 40% of pairwise registrations. Furthermore, SGHR achieved a registration recall of 99.8% on the outdoor dataset ETH, demonstrating its strong generalization ability. Then, we conducted an analysis of the reliability of SGHR's overlap estimation, which showed that it is able to distinguish reliable point-cloud pairs with high overlap. Additionally, for other multi-view registration algorithms, using SGHR's sparse pose graph can significantly improve the efficiency and accuracy of registration compared to using a dense pose graph. Regarding history reweighting IRLS, we conducted ablation experiments to verify the effectiveness of the proposed history reweighting function. Finally, we present some visual comparison results, where SGHR consistently achieves better registration performance. For more details and code, please refer to our open source website. Thank you for watching.